is very thin. All right, compare to the size of the bearing. All right, so that's why because the film thickness is too thin, and then when we compare with the diameter or the radius of this bearing, for example, so it seems like there is no curvature, right? It's just like a straight line, all right? So it's just like a straight line. Because why? Because the film thickness is too thin, all right? So that is the reason why the assumption number 8 is there, all right? So we continue again. Okay, so by the assumption number 8, allow the lubricant film geometry to be open out so that one bearing surface can be represented by a plane. So you have a plane here, which is an X and Z plane. So the Y will going in, all right? So there is no curvature, all right? No curvature. It's just like a flat surface, all right? Two flat surface. And let the H is the film thickness, all right? If we go back to the figure before this, okay? So H is the film thickness, L is the bearing length. So most of the time HL, H over L is less than 10 to the minus 2, all right? Often as small as 10 to the minus 4. It is very, very, very small, all right? The ratio is all 10 to the minus 4, but most commonly about 10 to the minus 3. All right, this is the ratio of it. Okay, because of that, we can say the lubricating film can be envisaged as a long thin channel of a small taper in all realistic bearing configuration. So okay, so this statement, we said that a long thin channel, all right, of a small taper is very important. So that's why we need to learn this viscous flow first and try to understand that we have two type of flow, right? One is coed, the other one is the Pose flow, right? Now, because why? Because it is a very slow moving fluid, and at the same time the moving is one of it is because of the pressure different. The other one is because of what? Because of shear stress. All right. So we have two type of condition. All right. So these two type of condition which create the flow of the fluid will happen inside the bearing. Some of the bearing, the fluid is moving because of what? Because the fluid being sheared by the journal, for example. All right. But some of the bearing said the fluid flow because of what? Because of two factor. Number one, because of the sharing of the fluid, and the other one is because what? At the same time, they have a pressure difference within that bearing. Okay, so the viscous flow will be applied into this lubrication. Okay, because of that, we can say even though we see the bearing is a circle, all right, almost like a circle. For example, if you have a journal bearing which is running inside the bearing, a shaft running inside the bearing, we see it is like a circle. But in terms of lubrication calculation, all right, because of this H over L is very small, so we can imagine it the clearance as the long thin channel. Okay. Next, the derivation of it. So we need to start with the definition. Let one bearing surface be represented by the plane z equal to 0, and the other by a curved surface such that the film thickness at any instant is a function of x and y. Okay, so we have a plane. All right, so the plane is such a film thickness is any instant, and then okay, so this is the plane. Okay, so this is what we call a z is equal to 0. So all this part here is z equal to 0, and the other by curves such as that the film thickness at any instant is function of x and y, not a function of z. Okay, and because of that, when we took the Navier-Stokes equation, all right, with all the 8 assumptions that we have there, all right, so all part of it will be cancelled, all right, all part of it will cancel, and also this rho gz is also cancelled because what? Because it is assumption number one. Okay, there is no number two. I think where there is no weight into it being taken consideration. Okay, and because of this cancellation, finally we have this assumption. The application of the assumption allow the equation of motion to be reduced to, so we have the partial p partial x equal to mu partial u partial u square partial z square, and then we have this in terms of y. Okay, and since we assume the pressure to be function of x and y only, okay, since we make an assumption that pressure to be a function of x and y, as we mentioned in the assumption there. All right, so this question can be integrated directly to give general expression for the velocity gradient. Okay, velocity gradient in this case, we okay. By the way, do you understand why it said that the pressure is a function of x and y? All right, so that statement is come from the assumption that we have just now. All right, I think on the slide number two. All right, so the assumption state that in the z axis, all right, in the z axis, all right, number one, the velocity does not change. All right, and then I think the viscosity also does not change. I think I'm not sure yet. But also the most important thing is that the pressure does not change in the z direction. So in other words, the pressure does not change in the height of the film thickness. All right. So since the pressure does not change in the z direction or the height of the film thickness, it means the pressure must be changed in either in x direction or in y direction. Okay, so that is the reason why you have the partial p partial x and then partial p partial y over here. And because of that statement, then we can say, okay, in that case we can rearrange the equation. All right, try to determine the velocity. All right, the velocity either u or v. All right, u in the x direction and the v in the y direction. Okay, because why? Because u because the pressure is the function of x and also a function of y. So when it is pressure is a function of x and y, it means the velocity, all right, the velocity will also depend on the in the change of that pressure in x and y direction. So that is the reason why we can integrate these two equation at the top here. All right, the two equation at the top here, and to determine the value or the equation for velocity in x and also in y direction. Okay. Integrate it once. All right. So when you integrate it once, so you have the partial u or partial z is equal to z over mu partial p partial x and plus a over mu. Okay, and also the same with the in term of v. All right, in term of v. So basically, by using the term that we have here, the partial p over partial x there, rearranged it, all right, in order to determine the velocity gradient. So we have this velocity gradient, one in x direction and the other one is in the y direction. Okay, where in this case a and c are a constant. So since it is a constant, so we need to determine what is the value of a and what is the value for the c. Okay, and now the viscosity of the lubricant may change across the thin film in the z direction as a result of the temperature variation we arise from bearing a problem. But for the beginning, let's treat mu as the average value of the viscosity across the film. Okay, so mu we can say it is constant across. All right, across in the z direction. By that statement, by that this statement does not restrict the variation of viscosity in the x and y direction. So by taking this consideration, all right, for the beginning, let's treat mu as the average value of viscosity across the film. Okay, and once again, if I can draw this is the x direction, all right, and then you have all this y direction. Okay, so the mu is constant. All right, the mu will be constant across this line. Okay, across the line blue here. All right, in the, if you have this Z, all right, in this case it's a Z, okay, so it is constant, all right, but okay, but this statement also does not restrict the variation of viscosity in the x and y direction. So in the x direction, probably we have change in viscosity, and in the y direction, probably also we have a change in viscosity. Okay, so by that assumption, so the velocity component now will become partial u partial z is equal to z over mu partial p partial a. All right, and when we integrate it twice or once more, all right, so you have this term, which is u is equal to z square over 2 mu partial p partial n and the rest, and also the same with the velocity in the y direction. Okay, so now if you want to know the velocity gradient in x and y direction, so we need to determine the A, B, C, and D, the constant. Okay, so in order to determine A, B, C, and D, we will discuss it in detail in the next video. But before that, all right, before that, let's imagine now. This is the plane that we have at the bottom in the figure here, which is x, y, and the z is equal to 0. Now imagine that we have two surfaces, which is the first layer of the bearing, and this is the top layer of the bearing. Let's say the first layer is at the z equal to 1, where the x and y is there. Okay, and at that point, and then we have another point on the second surface here. All right, on the second surface here, where the z2, all right, at the point of z2 here, we have a velocity 2 in the x direction and a v2 in the y direction, and then we have w2 in the z direction. Okay, so with all this figure that we have here and the boundary condition that we have here, from there we can find the constant of a, b, c, and d. Okay, up to that point. Okay, up to that point, do you have any question? Okay, because it's quite lengthy, all right, to create this Reynolds equation, all right, for the bearing, all right, but all the equation that we will create will based on the diagram or the free diagram that we have just now. All right, so it is important for you to refer it back, all right, and try to, what do you call it, uh, uh, create back the equation and try to understand the basis of it. Okay, don't just use the final equation, all right, because we need to go from the basic, all right, in order for you to design the bearing. Okay. All right, so we done with this the first part. All right, I make these short videos. All right, hopefully by doing that, you can repeat it a few times, all right, in order for you to understand it, all right. And you need to try, you need to write, all right, you need to write, and you need to try, all right, in order for you to feel it. If you don't, if you just watch the video and then you never try it, all right, you will not feel it, all right. You cannot feel, you don't have the feeling of creating that equation and how you want to apply that equation. Okay, so next I will share with you the second part of the video, because we have 5 parts, and I try to finish it today, or hopefully by next week we can straight go for the thrust bearing, all right, our first bearing, which is the thrust bearing. Okay, so let me have a look at this video. Okay, cancel that one. Hello, my name is Muhammad Zubir bin Bahak. Okay, and then I want to share. Device. Okay, share. And this is the second part out of five series of videos which will discuss in detail and explain how we derive the Reynolds equation. In the first part of this series, okay, we start with the Navier-Stokes equation and all the assumption that we have, and then finally we have the velocity component as the u equal to z squared divided by 2 mu partial p partial x and plus a z over mu plus b, and the velocity in the y component as shown, which is v is equal to z squared over 2 mu partial p partial y plus c z over mu and plus d. So we have four unknown, and in order to evaluate the unknown values, so we need to have a boundary condition. So let's say the coordinate system that we have as shown in the figure in front of here. Let's say we have a arbitrary surface. One is at the layer of z equal to 1, and the other is where the z 2. This is an arbitrary surface which is far away from the plane x, z, and y. And u1 and u2, v1 and v2, w1 and v2 is the absolute velocity of the surface at a given location as shown here, all right, the given location. And from there we can have the uh, boundary condition. For this case, for example, let the separation of surface Z2 and Z1 at the XY location considered to be denoted by H. Okay, so the separation distance between the Z1 and Z2, we call it as an H, and then from there, if you have the H, then at the point of x, y, and z1 here, over here at the bottom here, we have u equal to u1, v equal to v1, z and z1, and also the same for the point 2. Okay, so next we have the velocity in the x direction, all right, as just before, and then by putting all these boundary condition, we try to determine the a and b value. Okay, and for the condition, we find that the A1 as shown and B, C, and D. Okay, by putting all the boundary condition into the original equation, and then we solve for A, B, C, and D. Hence, when we combine all of that, finally we have this general velocity in x and y as the u equal to z minus z1 times the z minus z2 divided by 2 mu partial p partial x and plus the u1 times z2 minus z and divided by h and plus u2 z minus z1 divided by h. Okay, so this is a general velocity equation all right, for this coordinate system. All right, so that equation is just for this what we call a free body diagram or the coordinate system that we have here. All right, so where as the datum line z equal to z2. Okay, so by doing that, so we have the velocity, all right, for that particular surfaces, all right, is equal to the equation that we have here. Okay, so this is for general equation. All right, what we next what the next thing we need to do is to move the axis. All right, to move the axis. All right, from somewhere at the bottom. All right, we move it. All right, we try to move. Okay, let me show it back. All right, we want to move this egg y0 here. All right, from at the bottom somewhere here. Probably we want to put it here. All right, put it at a z equal to 1, or probably we put it at a z equal to 2, or probably we put it somewhere in between. All right, so what will be the equation will be created when we move that location of the original axis. Okay, so that will be discussed in the video number or video number 3. Answer this. Hello, Mike. Share directly for. My name is Muhammad Zubair bin Baha, and it's a part 3 of a 5 series Renault equation derivation videos. And part 3 here, we will discuss in terms of reference plane, all right, which we have discussed it in the part 2 of this series. In the part 2, we have derived the general velocity profile for two arbitrary surfaces of x, y, z1 and x, y, z2 as shown in the figure here. And we found that the velocity within the two surfaces there, all right, or we call it clearance between that surface at the bottom, the space at the top, is we found that u and v, the equation given there, where the h actually is the distance between that two surfaces, or we can say the h actually is the film thickness or the clearance. Okay, so what we need to do today, all right, in this video is to pinpoint exactly where is the z. All right, what happened if we move the z axis, all right, to a midway between the bottom surface and the top surface, and then we will try to move the z axis starting at the bottom surface. Okay, so that's the two that we will look in this video. And let's start with this. When the z-axis is in between two surfaces, it has been shown here. All right, so that this is the point where our z is equal to z over O, z equal to 0. Then the boundary condition. So we need the boundary condition to be put into the general equation that we have derived in the previous video. Okay, so at this point 1, we have u equal to u1, v equal to v1, and z1 equal to h divided by 2. It is the same as at a point 2 on the upper surface there. They have a 3 boundary condition there. Okay, so using this all 3 boundary condition, we put back into the general equation that previously defined in these part 2 videos. And from there we found that the velocity profile for these particular z-axis starting at the center of the clearance. All right, so the u, or the velocity in x and the y direction, and also the y direction is given in the box here. Okay, so we have a equation which is in this time it's quite different from the one that we have in the second part of the video. So the question is, where can we use this kind of equation? All right, where we can use this kind of equation. So basically, this equation, or we can say, if you putting the z axis starting at the center of the two moving surfaces, all right, which is moving relative to each other. So that condition is very useful, and it is already used for curved surfaces having identical geometry form, such as we have two spheres here. All right, so or we have a two cylinder. All right, if you take a point z is in between of these two clearance, then that velocity or the equation that we have is suitable for this type of bearing. See, okay, but as we mentioned, all right, as we mentioned in the class, we are more concentrating on the hydrodynamic. Okay, so this equation actually is suitable for what we call as the elasto hydrodynamic lubrication type of bearing. Okay, but our concentration is more towards the hydrodynamic lubrication bearing. So now let's see what happens if we move the reference plane containing the point of x, y, and z1. So in this case, we are moving the z-axis, and it starts at the point of z1. Okay, so if we go back to the picture that we have there, okay, so now our z was starting at that point, the right point here, okay, where in this case the z is equal to 0, then we will have this boundary condition at this point. The z1 is equal to 0, and then at the top layer of the surface there, we have another boundary condition. So taking all these boundary condition, put back to the general equation that we have for the Reynolds equation, then finally we found out that the u, all right, which is quite different from the one we have for the elasto-hydrodynamic lubrication. Okay, so we have the velocity in x and y direction for the fluid, all right, for the fluid moving within that two surfaces. Okay, and then this equation actually is applicable or suit for the the hydrodynamic lubrication bearing. For example, we have this journal bearing. All right, so that equation is suitable for journal bearing and also for the truss bearing. Okay, so now when we have the general equation for the hydrodynamic lubrication bearing, so we need to look more detail. Okay, how we want to use the equation? Can we expand the equation, or can we reduce the equation to suit the requirement of this hydrodynamic lubrication bearing? And that will be all right. So that will be discussed in the part 4 of this 5 series, Reynolds equation series, and we will create a general form, all right, of the Reynolds equation for what type of bearing? For hydrodynamic bearing, all right, for the hydrodynamic bearing. Okay, so now we almost toward the end of this topic. All right, to create Reynolds equation. All right, particularly for the hydrodynamic lubrication. All right, so we will go to for part 4 and also the part 5, where at the end we will have the Reynolds equation, which will become the basis of all the equation that we will create. All right, for the thrust bearing, general bearing, hydrostatic bearing, and step rally bearing, and the rest. Okay, so let's go for the part 4. Better cancel this. Share. Okay, we go for part four. My name is Muhammad Zubair bin Bahar, and this is a part four out of five part of this Reynolds equation derivation. So this video will be to create the general form of the Reynolds equation. In the previous video, we have discussed when we have the reference plane z equal to 0 containing the point x, y, and z1, which we have the boundary condition as shown here, the z equal to 0 at the bottom surface, and then the z2 is h above the point 1 at the bottom. And we have done the derivation, and finally we have the velocity of fluid in the x and also in the y direction as shown in the equation in front of you here. So next what we need to do is to take other consideration and put it together into the velocity of the lubrication. So we will look in terms of surface stresses, volume flow rate per unit width, and the x and y direction, and also we will combine the continuity equation. So when we talk about surface stresses, so viscous stress acting on solid as defined as the tau, where z equal to z1 and also tau equal to minus mu partial u partial z when z equal to z2 on the top surface. And but we have a u, all right, we have the u equation here where we have a partial p partial x and u2 z over h, and then hence if we say that the tau which is equal to mu and the differentiation of the velocity, so we differentiate the velocity u and put into the equation, then we have the tau at the z equal to z1 as shown at the bottom equation there. Okay. So now we just finished the velocity. All right. So now we know the velocity of the fluid between that two surfaces. All right. Which is let's say that it is moving. Maybe it is moving relative to each other, or maybe it's not moving relative to each other. All right. Because in this case, all right, if we just continue with the what you call the velocity only, all right. But whenever we move, all right, whenever we move, there must be a shear stresses, all right. So there must be a shear stresses. So that shear stresses need to be considered and be combined into the equation, all right. Uh, at the same time, all right, at the same time, we also need to combine the concept of the continuity equation, all right, as we mentioned in the previous slide, I think, all right, where we need to take consideration of the three factor here, all right, the surface stresses, and then the volume flow rate per unit width, and also the continuity equation. When you combine all these three into this the general equation of this velocity that we have just now, all right, then we will have a complete equation, all right, related to two surfaces, all right, moving, either both are moving on the same direction, or is it one is moving, the other one is not moving, all right, and sometimes probably both is not moving, but we have a pressure difference in between, all right. So all those being considered, all right. So that what we need to do now, all right. So we do it one by one. So we start with the surface stresses, and of course you know that the shear stress, all right, on the solid is a tau equal to mu partial u partial z, at the bottom there where the z equal to z1, and at the top you will have the negative, right? So because why? because at the bottom, if you put at bottom as the positive, at the top must be the negative. It will go to the other direction. Do you understand that? So that's why you have that negative value. All right. If at the top you're saying that the tau is equal to also positive, so there is no shear stress actually. All right. So the shear stress is happening when something is resisting the flow. All right. Resisting the flow. So that's why at the bottom make the assumption the tau is positive, while at the top the tau is on the other direction. Okay. Where z equal to z1 and also tau equal to minus mu partial u partial z when z equal to z2 on the top surface. And but we have a u, all right, we have the u equation here where we have a partial p partial x and u2 z over h, and then hence if we say that the tau which is equal to mu and the differentiation of the velocity, so we differentiate the velocity u and put into the equation, then we have the tau at the z equal to z1 as shown at the bottom equation there. Okay, what happened is that now you have u over here. All right, so you have the u equation here. All right, but tau actually is equal to mu, all right, partial u partial z. So you need to partial the or differentiate the u, all right, on the z axis. So we du dz this equation here, all right. After you du dz the equation, so you have this equation, all right. Okay, so that's why you have a mu here again, and we have a mu there at the end there. Okay, you differentiate the u equation here and put back into this tau equation. So tau now is equal to mu. If I put a parenthesis here, is equal to 2z1 minus h divided by 2 mu partial p partial x and minus u1 minus u2 divided by h, and we have the parenthesis, close the parenthesis at the end here. Okay. And then we put the tau at the z equal to z1 we have the equation here, but at z1 is equal to 0, so we rearrange the equation, then finally we have the tau equal to minus h divided by 2 partial p partial x and minus mu u2 minus u1 minus u2 divided by h, and for the z2 equal to h, you will have another equation. And next, from there, we would like to determine the volume flow rate per unit width in x and y direction, and we define the q per unit width as the integration of u dz. All right, so we do the integration because the flow is a non-uniform flow, so we have to do the integration. So we have the u. Okay, I hope you still remember in fleet one. All right, we have a Q, right? The flow rate is equal to V times A. Okay, if you still can remember that the flow rate Q is equal to V times A if you have a uniform flow. All right, where the velocity are the same from the bottom to the top. Okay, but in the real life, of course, you're not going to have that uniform flow. Most of the time, it is a non-uniform flow. And if you still remember, in order to determine this volume flow rate for the non-uniform flow, you need to integrate the U or V dA, isn't it? Okay, I hope you still can remember what you have learned in fleet one. So we applied it here. All right, so we applied it here. Equation, and we put into this q or the volume flow rate per unit width equation, and then we do the integration, and finally we have the qx is equal to minus h cubed divided by 12 mu partial p plus u1 plus u2 divided by 2 h, and do the same for the y direction. Thus we have the qy It's almost the same, but change in term of v. All right, u will change into the v. Next, we have a continuity equation. All right, we want to join this continuity equation with the velocity equation that we have. If you can remember that continuity equation in Cartesian coordinate as shown here, partial rho, partial t, and we have the partial rho u over partial x, and the rest. And if we put this continuity equation in term of integral form, so you have the second equation at the bottom there. Okay, then this continuity equation must equal to 0. And we have a general rule for integration. If you have integration of partial something, all right, and in terms of dz, then we have this rule of thumb how the product of that integration. Okay, this general rule of integration, of course, I think you learned it in mathematics, somewhere in mathematics, not in our class and not in fluid mechanics class, I think. All right, so I just pick up this general rule of integration and applied it here. All right, so in other words, what you learn in mathematics is being used here. All right, to create another equation. And then we use this product of integration into the continuity equation with the integral form. And from there, if we assume, make the assumption that rho to be the mean density across the film, the integrated continuity equation will become as shown there. But if you remember, okay, the integration of z1, z2, u dz is equal to qx, and integration v dz is equal to dy. And if you look into this continuity equation in term of integration, we have the term of integration u dz and in the term of integration v dz. So volume flow rate per unit width that we have there and put into the equation. And finally, we have this long equation here, which this equation, the top one is the top one represent the rate at which the mass is being lost from the control volume due to the pose, that is the pose part there, and because of the quiet flow velocity. Okay, so now we have term which is pose and quiet together, which is represent the rate at which the mass is being lost from the control volume. And the second part of this equation, all right, this red line here represent the conservation of mass for the fluid, or we can say that this is the squeeze term. All right, so this 1, 2, 3, 4, 5 term here represent the squeeze term, the rate which the mass is accumulating within the control volume due to the change in height of the column. The resultant of surface velocity in the z direction are, if we have here w2 minus u2, partial partial z2 partial x, and we have w1 minus u2 partial z1 over partial x. So the rate of change of the height of the column is w2 minus w1 plus u2 partial z1 over partial z, and minus u partial z2 over partial x. And the last term of this equation, all right, we call it as the local compression, which is h partial rho partial t is equal to z, is represent the rate of the increase of mass in the column of height h due to local density change. All right. Okay, panjang tak dia punya equation? Alright, it is a very long equation, and then it is combining, yeah, it is combine the pressure and also because of the shear stress, right? So that's why you have this pose and also quiet. At the same time, you have this squeeze term, no? All right, and then lastly, you have this local compression. All right, so by combining all of this, all right, it means that the whole thing that happening within that small what do you call it, a small area, all right, has been considered. Okay, so when you look back into this equation, it seems like, right, it seems like we talking about what? A boundary, not boundary. We talking about what we call the control volume, right? If you still remember the is it fleet one, all right, where you learn about this Reynolds transport theorem, and also the control volume. Okay, so we apply it here now, all right, in practical, all right. We're doing it in a real problem, all right, related to bearing. And if we have a density change, so this equation represent the conservation of mass for the fluid. So we have the first part of the equation represent the rate at which the mass is being lost from the control volume, and then the second part we have the squeeze term represent the rate at which mass is accumulating, and then the third part of the equation we call it is the local compression, which represent the rate of increase of mass in the column of height h due to local density change. And the Reynolds equation in general form for the fixed axis, okay, the fixed axis actually, we just repeat the same equation. And then if we put in terms of 2D equation, so you have this equation which consists of posy, coit, and you have your squeeze there, and also the local compression. Okay, so partial rearrange the equation actually. We have the posy on the left side, and the rest will be put into the right side of the equation. Okay, so that equation is quite too long, where you have to take consideration of the local compression, you have to take consideration of the squeeze term. Okay, so some of that is not that applicable for our purpose. So we need to have a standard equation. All right, so we need to have a standard equation which is more applicable to different type of machine. Okay, so that will be discussed in the last part of this Reynolds equation derivation videos with the title of the standard equation. Okay, so for those who like to, all right, for example, if they want to continue their study in master degree, for example, if you want to know really what really happened, right? If you go to basic, right? If you go to the basic, and then you have bearing, and you want to consider all right, consider all these posing, co-weight, squeeze, local compression, and density weight, stress, physical weight. All right, all of this can be analyzed or can be solved using the CFD, right? By using the CFD, of course, you can solve this or analyze the problem, right? Not by hand, because the changes there, all right. Probably we say if the density change, for example, all right, it will give a huge impact to the result. Okay, so we go for the last part of this Reynolds equation, all right, which is the video number 5. We try to uh, create the last equation, all right, the simplest equation, not the long long equation. uh, if we have that kind of equation, which is a very long equation, probably nobody want to take this lubrication, right? Okay, so we will try to make it shorter and meaningful, all right, to be used. All right, so let's go and check this last video. Hello. Okay. My name is Mama Zubibimba, and this is the final part of a 5 series video discussing the derivation of Reynolds equation. In the previous video, we make a reference of z point at the z equal to 1. With that, we have the boundary condition as shown, and then we put it into the general equation of this Reynolds equation, and finally we have this a particular long Reynolds equation which consists the pose, the coil, the squeeze, and also the local compression. And in this video we will try to find the reduced form of this Reynolds equation, which we can apply easily uh, to the bearing, real bearing. So if we only have tangential motion, for example, where the W2, which is the velocity in the z direction, uh, the top part of the surface is moving in in that z direction, while the W1 is not moving, then the Reynolds equation be reduced to Okay, so if we only have tangential motion, in this case, I mean, do you remember the surfaces? We have two surfaces, right? And then that two surface, the x direction is from the left to the right, while the y direction is from the screen into the screen, right? And then the z direction is upward, okay, from bottom up, okay. So what happened now is that let's make the assumption that the surface at the bottom is fixed, all right? It is not moving. It is fixed at the z equal to 0, all right? It is not moving. But we give the opportunity for the second surfaces or the top surface to move, all right? So this is the real condition of the bearing. All right. Bearing, we have the housing, which is not. We can say that it is in static condition, while the bearing. All right. We have housing, and then the bearing itself. All right. They have the ability. All right, to float. All right, to float. When it is to float, it means it will move in the z direction. All right. So in this case, we make the assumption that W2, all right, have the equation, while the W1 is equal to 0. Okay, so we fix one. All right, the other can move in that direction. So by doing that, so we have the equation that you have in front of you now. The equation at the bottom there, and then so Reynolds equation can be written as the one that you have in front here, which is the partial rho over partial x rho h cubed divided by mu, and then you have in term of y, and then if it is equal to 12 times the u bar, and also plus the 12 bar, where this u bar is equal to u2 plus u1 divided by 2. Okay, so the u bar is the velocity of the top surface plus the velocity at the bottom surface, which is equal to 2. But please remember that most of the time, our bearing is only one part of the surface moving, the other part is not moving, which is a static. Okay, I think this U bar equal to U2 plus U1 divided by 2, and V bar equal to V2 plus V1 divided by 2 is been, I think being used, right, in the viscous flow condition, right? So you have this U bar and V bar. So please make sure that you remember this equation here, all right? Because it is important that U bar there is defined as U2 plus the U1 divided by 2. What is U2 and U1? U2 is the top surface moving in x direction, and U1 is the bottom surface in x direction. If at the bottom there it is moving, if it is not moving, so the U1 is equal to to 0. Okay. Okay, so this is question, all right, which is a box is there, is applicable for elasto-hydrodynamic lubrication. All right, so this elasto-hydrodynamic lubrication, which is consists of, for example, the ball bearing, and then you have this cylinder on cylinder or sphere on sphere. Okay, I can use this reduced equation. of a Reynolds equation. Okay, but as mentioned in the beginning of this videos, our concern is more towards the hydrodynamic lubrication. So how about the hydrodynamic lubrication? So for this hydrodynamic lubrication is applicable, for example, for the journal bearing and also on the thrust bearing, which is on the right side here. Okay, for the hydrodynamic lubrication, the fluid properties do not vary significantly throughout the bearing, and thus may be considered to be constant. Okay, so fluid property do not vary significantly throughout the bearing. Okay, so for hydrodynamic lubrication, the motion is a pure sliding. Okay, pure sliding. It is not rotating. It is just a slide. Okay, the top surface slide on the bottom surface. Okay, so in this case, even though let's say you see the journal bearing, right? So the journal bearing it is rotating, right? The shaft is rotating inside the journal is the journal is rotating inside the bearing, right? The housing we call it bearing there. Okay, so uh, but the statement that we have in front of you now is state that uh when we have this hydrodynamic lubrication, all right, the motion is a pure sliding, right? It just slide there. Even though we see it seems like it is rotating. Okay. Because why? Because of this the film thickness is too thin. All right. When it is too thin, it become what? The curvature is not there, right? The curvature is not there. So even though we have 360 degree, so every point of that 360 degree is just like something, a surface sliding on another surface. All right, so that's why we call it as the pure sliding. Okay, even though the machine actually is rotating, but the shaft is not rotate on the fluid, but it is sliding on that fluid. Okay, so that's why, and then after that, when it is slide, all right, when it just slide in one direction, it means there is no velocity in y direction, right? Because it is slide in x direction. If you can imagine, right? Because let's imagine over here is the egg. If you can see my pointer here. All right. So the egg direction is from the left to the right. While your z direction z direction is from the top from bottom to bottom up, and then the y is into the screen. Okay. So when you have the shaft rotating, all right, it is rotating. Actually, it just slide. All right, purely slide in x direction. So when it is sliding, so the whole side of the fluid will move in one direction. All right, and that direction is in the x direction. So in that case, there is no velocity in y direction. Where in this case we can make the assumption that the velocity in the y direction is also equal to zero. So the only velocity that we have is a velocity in the direction of surface movement, which is in the y direction. So with that, uh, the Reynolds equation now can be reduced to partial over partial x h cube partial p partial x plus the partial over partial y h cube partial p divided by partial y equal to 12 u bar mu partial h partial x. And this equation allows the fluid properties to vary in x and y direction and also permit the bearing surface to be of infinite length in y direction. So this equation allow the property to vary in x and y, and at the same time we can make the y length in terms of y direction become infinite. So when it become infinite, the side leakage or the flow in the y direction, which is associated with the second term of this equation, can be neglected. So in many conventional lubrication problems, side leakage can be neglected. So the term y, the y term in the equation can be eliminated. Okay, so then after taking that consideration, once again, this equation for no side leakage, all right? No side leakage. There is no velocity in y direction. So the reduced equation for the hydrodynamic equation now will become partial over partial x rho h cube divided by mu partial p over partial x is equal to 12 u bar partial rho h divided by partial x. So this is the important equation that will be used to analyze the thrust bearing, general bearing, and probably we have this step bearing. Okay, so the integrated form of Reynolds equation, but we are looking for the pressure, the pressure difference along the x direction. So the equation that we have just now, we need to be integrated and find the equation of dp over dx. So start by integrate the north side leakage Reynolds equation with respect to x. And then you have this 1 over mu dp over dx is equal to 12 u bar divided by h squared plus the a bar divided by rho h cube. And we have a constant a, and then in order to determine the value of a constant a, once again, we have to define the boundary condition, which is dp over dx is equal to 0 when the x is equal to xm, which is at the maximum point of pressure different. The x is equal to xm. At that time, the rho is equal to rho m, and also the h is equal to the h maximum. So, taking this boundary condition, put back into the product of the integration, then we have the a as the minus 12 u bar rho m hm. Thus, the product of the integration of the Reynolds equation is equal to dp over dx is equal to 12 u bar mu rho h minus rho m hm divided by rho h cube. So this is the integrated form model of that particular Reynolds equation. And the subscript m refer to the condition at all point where dp over dx is equal to 0, such as the point of maximum pressure. And the most used integrated form of Reynolds equation is when we can make the assumption that the rho, the density of the fluid, is constant throughout the bearing. So when you have that rho constant, then the final equation is equal to dp dx equal to 12 u bar mu h minus hm divided by h cube, and this equation is applicable for hydrodynamic lubrication bearing such as thrust bearing, the general bearing, the step bearing, and this also will be used, all right, in the next video when we discuss about the thrust bearing and also in the general bearing. So this is the final equation that we are looking for and that we can apply for the analysis of lubrication uh, for the hydrodynamic bearing. Okay, guys. All right. So you see, we start from the very what we call it complicated Navier-Stokes equation, right? And then we apply to the what arbitrary surfaces. All right, and we have such a long equation, right? Okay, so I still remember when I took this class last time. When I saw that equation, I said, "Oh my God!" All right, it is almost the end of my world then, right? Because it is very long, and then it's quite hard for us to try to understand it. Okay, but by the end, when I saw, the last question that we need to do is what to use is what dp dx is equal to 2f mu bar mu h minus hm divided by h3. Oh my god. All right, so and then I feel, well, I think I can go ahead and do the analysis using this equation because it is quite a simple equation. All right, so hopefully when you watch the video, all right, the process, all right, the process of getting this final equation. At least you will appreciate what is the meaning of this dp is equal to 12 mu bar mu and h minus hm, and then divide by hq. All right, so next week, all right, which I'm not sure whether we will have the class on Monday or not, all right, because it will depend on the what the new government will say. All right, probably we'll have another holiday then. Okay, so the confirmed day that we will meet, it will be on the Wednesday, right? So on the Wednesday we are uh, confirm what you call it, having a face-to-face class, and we will start with the uh, trust bearing. All right, we will use the Renault equation. We just found it today. All right, and then we will apply it into the thrust bearing. So we need to go slow one by one, okay? And today I need to put all the information together, even though Muhammad Afif said it the full already. Okay, but I will share the video. All right, you need to watch it one by one. If you still cannot understand it, you don't have to create that equation. All right, you don't have to create the equation, but at least you know where the equation come from. Okay, and when you know the basic, and then you can play around with the mathematics, and probably you can do others. All right, and apply it somewhere. All right, you can apply it somewhere. Okay, guys, I think it is already 3:26, almost 3:30. Okay, and as I mentioned to you that I'm not sure what will happen on Monday. Okay, if on Monday, all right, if on the Monday say okay, on Monday there is no holiday. Okay, but on Monday you still have not, is it cuti? Not a cuti, right? Is it cuti on Monday? Or it is where the student don't have to come to them. By the way, all right, I will check. Okay, I will check and make a confirmation. All right. If in case, all right, if in case it's not cuti, not on holiday, but you still have a class, your class of course will be online. Not going to be face to face. All right, because throughout this week, all the class must be online, and I'll probably include the on Monday because Sunday is holiday in Johor. All right, and then Monday I will check back. Okay, if it is cuti, then I'll see you back on Wednesday, and prepare yourself for another mathematics. All right, so lubrication is a mathematics class, all right? It is a mathematics class, but don't worry, all right? So I will show you, I will show it to you. Not that simple, but I'll show it to you how to solve it, okay? And I think everybody can do it, all right? Everybody can do it. All right, so I think we better stop here. All right, have a nice weekend. All right, make sure take care yourself. All right. If you are eligible for to vote, you can go and vote. All right, and make your own decision, a correct decision for the rest of next 5 years. All right, which will give impact not only for 5 years, it will give impact to throughout the world, right? Okay. So your vote is not for 5 years. All right, your vote is for the rest of this world. Okay, so think it carefully. All right, read all the information. Don't just read in just one side. You need to read the whole side. All right, and then make your decision. Because why? Because you are an educated. All right, you are educated, so you need to balance. All right, you need to balance. Okay, guys. I hope I will see you again in good health on next Wednesday. All right. Okay. But based on, yeah. Okay. 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 Selamat mengundi to everybody. Okay. Bye bye.
You too.
Assalamualaikum.
Can you share